Welcome to the lecture series on optics. So today we'll be starting with the unit of polarization, and this is the first lecture in the unit. And we will be covering the topics of longitudinal and transverse waves, polarization, its definition, types of polarized light, polarization by reflection and other means, Brewster's law, pile of plates, Malus law, dichoric crystal, double refraction, optic axis, principal section and planes, and Nicol prism, and different versions of Nicol prism also. So we start with the definition of longitudinal and transverse waves. The longitudinal waves are those waves in which the particles of the medium travel in the direction of the motion of the wave. Since we know that wave is a traveling disturbance and the particles of the medium vibrates and the energy is transferred by means of the vibration of the particles about their mean position. So if the particles of the medium travel in the direction of motion, then the wave is longitudinal. And if the particles travel in a direction perpendicular to the direction of the motion of the wave, then the wave is called transverse. Light is a transverse waves, and it has two vibrations. One represents the electric field and the other represents the magnetic field. And both these electric and magnetic field vibrations are perpendicular to each other and also perpendicular to the direction of propagation. So these electric and magnetic vibrations can occur in numerous planes. A light wave that is vibrating in more than one plane is called unpolarized light. See that primary requirement for transverse wave is that the vibration should be in a direction perpendicular to the direction of propagation. If we consider a three-dimensional uh, coordinate plane, then we can see that we have three directions, x, y, and z. So if the light is propagating in the z direction, not in the direction, but along the z axis rather, then the two perpendicular directions will be the x-axis and the y-axis. So we have two field vectors. One is electric vector and the other is magnetic vector. One should be along the x-axis and the other should be along the y-axis. It can be either of the two. X-axis, we can have the electric field or the magnetic field, and the other one will be along the y-axis. You just see, when we compress a spring, the disturbance is traveling along the direction of motion. So the wave is longitudinal. What happens? So the wave is traveling along the direction of propagation, and notice this particle. If the particle is vibrating along its mean position, the particle is not traveling, but the wave is traveling. Notice this. If we move the hand upside down, that is in a direction perpendicular to the direction of propagation, the wave travels in this way. The vibrations are in the direction perpendicular to the direction of propagation, and the propagation is in that direction. Now we come to polarization. Since we discussed that there can be numerous numbers of planes of vibration, the only conditions that are there are that the direction of propagation, the electric vector and the magnetic vector. The electric and magnetic vector should be perpendicular to each other and should also be perpendicular to the direction of propagation. So if since there are numerous possibilities and these possibilities are randomly explored, then the light is said to be unpolarized. But if we define a plane, like here we are saying that the electric vector can be like along this line. But if we define the direction, a particular direction, it can be this or it can be this. If we define a particular direction, then the light is said to be polarized. Here the vibrations lie in one single plane only. And the polarized light waves are light waves in which the vibration occurs in a single plane. And the process of transferring the unpolarized light into a polarized light is known as polarization. You just notice this. There are two vibrations. One is along this vertical direction and the blue one is along the horizontal. The light coming out of the polarizer has only one vibration, that is in the vertical direction, the yellow one, and the blue one has not come outside. The blue one has been polarized, and now we are getting in the polarized light only one vibration. So we have three kinds of polarized light. One is the linearly polarized, linear polarization. The other is a circular polarization, and the third one is the elliptical polarization. Consider this table. First, we take the linearly polarized light. The amplitudes can have any value, but the phase difference between them will be either 0 or pi. Just see these two. This is a transverse wave. The oscillations are in a direction perpendicular to the direction of propagation. We say that this is the electric vector. This is the propagation of the electric field only. And the electric field along the x direction is represented by this expression. And the electric field along the y direction is represented by this. This is the phase difference between the two vibrations. If this phase difference is either 0 or pi, then it will be linearly polarized. How? Let's see to it. If we substitute this kz minus omega t as this capital theta, then the first expression reduces to this one. And the second one will be reduced to this one, since I said that the phase difference is either 0 or pi. So it will be cos theta plus pi or theta plus 0. In that case, it will be sine capital theta. Now we will square and add these two equations. We get this equation, which is the equation of a circle. So this is the circularly polarized light. If Ex is equal to Ey and the phase difference is plus pi by 2, then the equation will be reduced to the equation of a circle and the light will be circularly polarized. Now let's come to the third case. Yeah, one more thing. There are two chances. If it is plus pi by 2, then it is left circular. And if it is minus pi by 2, it will be right circular. That means the direction of the rotation. We will, this thing will be clarified when you see the next figure on the next slide. Now let's come to the case where Ex is not equal to Ey. If Ex is not equal to Ey, then the right hand side will not be 1. This will not be 1. So then in that case, it will be the equation of the ellipse. And circle is what? It's an ellipse where the eccentricities are equal. Circle is a special case of an ellipse. So similarly here, if it is the phase difference is arbitrary, then it is ellipse. If the phase difference is pi by 2, then it is circular. Just look. Here, this is the linearly polarized light. You see the locus is circle, and here it is ellipse. See the direction of the motion. This is moving in clockwise direction, so it is right-handed polarization. It is moving on the right side. If the circle moves on the left side like this, then it will be the left-handed polarization. Similar will be the case with the elliptically polarized light. And these polarization can be done by 4 methods. First is the transmission, reflection, scattering, and refraction. See, by transmission, what we mean, if we have two slits, vertical slits, and we pass a rope, we see that there are vertical oscillations. These passes with both the vertical slits. If we turn this slit, make it horizontal, and the vibrations are the same, they will pass through this vertical slit, but will not pass through this horizontal slit. So, similar will be the case with the polarized light. This light is unpolarized, it is passing as such. Here we are restricting the oscillations. So the light we get will be polarized light. So in polarization, we have to restrict one of the oscillations. Similarly, the polarization by reflection, what we mean, that if a reflection takes place from a denser medium at a certain angle, and that angle is called the Brewster's angle. So if a diffraction is taking place from a denser medium at the Brewster's angle, the reflected light will be partially polarized. Now let's see scattering. If an unpolarized light is coming incident on a molecule, then there will be two beams. The beam which is going on as such will be the unpolarized light, and the scattered beam will be the partially polarized one. And if the angle is 90 degree, then it will be a polarized. By diffraction, we mean that if we take a crystal of calcite or quartz, then there is a phenomena that the incident light is broken into two. One is with the vertical vibrations and other with the perpendicular vibrations. And we will discuss this phenomena later on. One is called the extraordinary ray and one is called the ordinary ray. This phenomena is called double refraction. We will discuss the phenomena later. So let's consider polarization by reflection. This was discovered by Malus in 1808, and he said that if a beam of white light is incident at a certain angle on the polished surface of a metal or ordinary glass, it is found upon reflection to be plane polarized. See, if a beam of unpolarized light, AB, is incident at about an angle of 57 degree on the first glass plate B, this is reflected again at an angle of 57 degree by this and will be incident on the second glass plate, which will again reflect it at the same angle. And so in this way, we will have the output wave, which is quite parallel to the input one. If we rotate the upper plate about BC as an axis, this is the axis, and we rotate this on this axis, then the intensity of the beam here is found to decrease. And it will be such that when the angle of rotation becomes 90 degree, there is no output beam here. So the rotation about BC has kept the angle of incidence constant. The angle of incidence has not changed. The beam is coming on this path only, and this is at this angle only. The only thing is that it is in circular motion. So if the angle of the incidence on either the lower or the upper mirror is not 57 degree, the twice reflected beam will go through maxima and minima as before, but the minima will not have zero intensity. If we change the angle, then the intensity will vary, but it will not become zero at any instant. It will have a variation between a maxima and a minima. So the angle at which we get complete extinction of light, that means the light of the wave coming out here is totally polarized. That angle is called the polarizing angle or the critical angle. The polarization by refraction, as we said, that If the light is reflected at the Brewster's angle, a certain angle that is called the Brewster's angle, the reflected beam is polarized. So this is the Brewster's law. And the expression for this, if phi is the angle of the incidence, then tangent of that angle is equal to the refractive index. So the Brewster's law shows that the angle of incidence for maximum polarization depends only on the refractive index. There is no other quantity. So it depends totally on the refractive index of the reflecting medium. Now we come to the reflection by the pile of plates. We have simple glass plates placed one above another. And if a beam of ordinary light is incident at the polarizing angle on the pile of plates, this is the unpolarized light, this is incident at the polarizing angle on these pile of plates, some of the vibrations perpendicular to the plane of incidence are reflected at each surface. Here some are reflected, some will be reflected from other surface, from this surface some will be reflected, and so on. And the resultant one will be that what we'll get after a certain number of plates, that all the vibrations in the perpendicular direction have been reflected, and what is remaining is the vibration in the other direction only. So this light will be polarized, what we are getting after multiple pile of plates, after passing through multiple number of pile of plates. And this degree of polarization of the transmitted light can be calculated by summing the intensities of the parallel and the perpendicular components. If the parallel is the IP, parallel intensity, and the perpendicular one is the IS, then this is the expression for polarizability. And M is the number of the plates and N is the refractive index of the plates. Since all plates are made up of same material, so the refractive index will be same. So this is the polarizability. And we can approach about 100% of the polarizability by using this method. The another law is called the law of Malus. This states that how the intensity transmitted by the analyzer varies with the angle that its plane of transmission makes with the polarizer. And it says that the transmitted intensity varies as the square of the cosine of the angle between the two planes of transmission. Its proof is that any polarized, plane polarized vibration, let us say that the one produced by our polarizer can be, this can be resolved into two components. One parallel to the transmission plane of the analyzer and the other to the right angles to it. Let A represent the amplitude transmitted for the by the polarizer for which the plane of transmission intersects the plane of the figure in the vertical dashed line. When light strikes the analyzer, one can resolve the incident amplitude into two components, A1 and A2, the latter of which is eliminated by the analyzer. And the amplitude of the light that passes through the analyzer is therefore given as A1 is equal to A cos theta. This is the horizontal component. So this one will be A1 cos theta, and this one will be A cos theta, and A2 will be equal to A sin theta. So we are concerned with this. This A1 is equal to A cos theta. So the intensity of this particular component will be square of the amplitude. It will be square of the amplitude A1, which will be equal to A square cos square theta. And this A square is equal to the amplitude of the incident radiation. So the square of this amplitude will be the intensity of the incident radiation. So in this way, we can see that the output intensity is equal to the input intensity multiplied by the cos square theta. There is other method known as the polarization by dichoric crystals. So what are dichoric crystals? So these are the crystals having the property of selectively absorbing one of the rectangular components of the ordinary light. There are two components, so they will absorb one and transmit only one, the other one. So obviously the output light will be polarized. And this is exhibited by a number of minerals and by some organic compounds also. And the best crystal of this kind is called tourmaline. So what happens exactly is, if we take two crystals, we see, and having the same axis, when they are in the same, we place them in the same direction, then we see that the unpolarized light is coming. And up from the first, it absorbs the second component, only the perpendicular ones are coming out. And from the second, which is in the same direction, this light is going as such. If we turn on this second one in a direction perpendicular to the first one, then we see, that means they are crossed, then we see that no light is coming, because this was already polarized and this component has, the axis is now in this direction and this component has been stopped by this. So in this way, we can see, we can test the polarization. This is the test for polarization. We have two crystals of the same kind. When they are in the same direction, the light we are getting is polarized. When we rotate the second one by 90 degrees and we don't get any light, that means the light which was coming was polarized. And this was invented in 1932 by Land and is used in many of the optical instruments, like thin sheets of nitrocellulose packed with ultra microscopic polarizing crystals with their optic axis parallel. And these are used in the polarized glasses that you wear and different kinds of gadgets. Now, as we saw, polarization by refraction, so that is double refraction. And there are certain crystals, mainly there are two crystals, calcite and quartz. Both these crystals are transparent to visible as well as ultraviolet light. And the calcite crystal is chemically calcium carbonate, which occurs in a great variety of crystal forms, but it readily breaks into simple cleavage rhombohedrons. This is a rhombohedron. So this calcium carbonate breaks into this kind of crystals easily. Each face of the crystal is a parallelogram whose angle are 78 degree 5 minutes and 101 degree 55 minutes. The other one is the quartz crystal, which is chemically pure silica, SiO2, silica oxide. So when a beam of ordinary light is incident on the calcite or a quartz crystal, there will be, in addition to the reflected beam, two refracted beams in place of the usual single one observed. And these two, conversion of one incident beam into two refracted output beams, is called double refraction or birefringence. You can observe this if you put a dot on a piece of paper and put the crystal just above the dot and observe from the upper side. You will see the two images of this dot that we have placed here. And if you move your head, you will see that one of the images is stationary, while the other image is moving. The other image moves. The one which moves is called the extraordinary ray, and the one which is stationary is called the ordinary ray. Upon measuring the angles of refraction for different angles of incidence, one finds the Snell's law for diffraction. And the ray, like I said, one of the ray will be one of the image will not be moving, that is the ordinary ray, and all the laws of optics will be valid for that ray. While the other one which is moving is called the extraordinary ray, and the laws of optics are not valid for this ray. Since the two opposite faces of the calcite crystals are always parallel, the two refractive rays emerge parallel to the incident beam and therefore parallel to each other. Inside the crystal, the ordinary ray is always to be found in the plane of incidence, and only for the special directions to the crystal is this true for the extraordinary ray. If the incident light is normal to the surface, the extraordinary light ray will be refracted at some angle that is not zero and will come out parallel to but displaced from the incident beam. The ordinary ray will pass straight without any deviation. So a rotation of the crystal about the ordinary ray will cause an extraordinary ray to rotate around the fixed ordinary ray. And the axis along this happens is called the optic axis of the crystal. So let's define optic axis. So what we saw that calcite and quartz are the two anisotropic crystals. Anisotropic means that the property of the crystal changes with direction. So there are two examples chosen to show the simple type of anisotropy which characterizes the uniaxial crystals. In these, there is a single direction called optic axis. Single direction, that is why they are uniaxial. There is a single direction called optic axis, which is the axis of symmetry with respect to both the crystal form and arrangement of atoms. And if the light passes through along this optic axis, it will pass undeviated. That means it will not be polarized. A light passing through the optic axis will pass unpolarized. And if a light is passing through any other axis, it will be polarized. And the direction of this optic axis in the calcite is determined by drawing a line x dash through a blunt corner of the crystal. This is the blunt corner, this one, so that it makes equal angles with all the faces. So this also happens to be the axis of symmetry. If we rotate the crystal along this axis, if we rotate the crystal along this axis, it will rotate symmetrically. So such kind of axis is called the optic axis. It should be emphasized that the optic axis is not a particular line through the crystal, but a direction. So like you have drawn this line. So it is not necessary that light is passing through this line only. The direction should be the same. It can be any of the axes. Principal sections and principal planes. So the principal section is the plane. It is made by the plane containing the optic axis and normal to any cleavage face. For a point in crystal calcite, there are three principal sections out of each pair of the opposite crystal faces. A principal section always cuts the faces of the calcite crystal in a parallelogram with the angles at 71 and 109 degree. And the principal plane of the ordinary ray is the plane containing the optic axis and the ordinary ray, while the principal plane of the extraordinary ray is the one containing the optic axis and the extraordinary ray. The principal planes of the two refractive rays do not coincide except in special cases. Under these conditions, the plane of the incidence, the principal section, and the principal planes of the ordinary and extraordinary rays coincide. Here you see that they are coinciding, here they are not. Start with Nicol prism. If we take a crystal whose length is 3 times the width, and the principal section is cut about 70 degrees, it can be 68 or 71. Such a crystal is we are taking, and we cut the crystal along this plane, along the transverse plane, and again we paste these two pieces by a chemical known as Canada balsam. The refractive index of this Canada balsam is such that it falls in between the refractive index of the ordinary and the extraordinary ray. So what happens since it is less than the refractive index of the ordinary ray and greater than the refractive index of the extraordinary. So after pasting, what we observe that if a unpolarized light is incident on the crystal, it is broken into two. One is the ordinary ray and the other is the extraordinary ray. The ordinary ray being having the higher refractive index is reflected at this by this layer, while the extraordinary ray having a lower refractive index passes through the crystal, through this layer and then through the second part of the crystal and goes through it. So we are eliminating one component. We are allowing the extraordinary ray to pass and blocking the ordinary ray and getting the ordinary ray along this direction. So this is the device that is constructed to get a polarized light through the process of double refraction. And in the previous Nicol prism, we were not having any restriction about the direction of the optic axis. The optic axis of both the parts of the crystal. This was the same crystal. We cut it and then paste it with a layer of Canada balsam. Now we take two crystals, different crystals. Here in one, the optic axis is in that direction, and the other one, the optic axis is perpendicular. Now if we paste the one having optic axis horizontally and the other having horizontal optic axis in the perpendicular direction, then we get these two possibilities. Either first part will having the optic axis horizontal and the second not, or the first will having it in the perpendicular direction and the second will have in the horizontal direction. If the first part is having the optical axis in the horizontal direction, then what we will get is the ordinary light going straight and the extraordinary light coming out at an angle. And if the optic axis of the first part is in the perpendicular direction, then the ordinary and the extraordinary light both will be deviated from the main axis. And this prism, in which the first one is having the optic axis in the parallel direction, is called the Rock-on prism. And the second one, in which the first part is having the optic axis in the perpendicular direction, is called the Wollaston prism. And we end our lecture here. And I hope that the topics that we discussed right now will be clear to you. And any of the difficulties, just leave it in the comment and I will respond to you. And please like the video and subscribe to the channel. And shortly we'll be coming up with the next part of the unit, so the second part of polarization, which will cover the remaining topics. Thank you. That's all for today. Thank you.